Hello, and welcome. AP Chemistry, Unit 5 review. Hello, Zach. How's it going? How's it going? Excuse me. Rates. Let's see. We got 5 people in here. Where's everybody else? Slow. How's studying been going? You guys ready to take the test? We've got what, 3 weeks? Yeah, 3 weeks till the test. 3 weeks. I'm working on a calendar for May that I'll have out to you guys probably tomorrow in an email. So you can kind of expect what we're going to do for the rest of the school year. They just announced yesterday that we're supposed to be finished teaching. The last day that we should be giving new material is the 15th. So we'll have to kind of figure out what we want to do with that. Anybody start the 2017 for your response yet? Yeah, I'm gonna be having class on Friday, Lauren. I know that a lot of teachers aren't, but I still am. If you can't make it for whatever reason, just watch the YouTube video. But I'm gonna teach. I mean, we only have like 3 weeks till the AP test, so I don't want to miss any. I don't want to miss any chances to teach. So I'm gonna use every minute that I can. So yeah, I'm gonna teach class on Friday. So expect class Friday. Yeah, technically it's not a day of school, but what's a day of school these days? What is school, right? Yeah, basically. That's my idea. I mean, otherwise I'd just be bored. But, yeah. Hey, David. No. I mean, it's the same idea. I stream same with Monday. Oh, shoot. I forgot to change the time. Struggling today. Oops. Your professors don't even teach anymore. That's ridiculous. Everyone's like just giving up. That's crazy. I still did it for everything. No, my calendar, it's similar for Honors Austin. I stream in the morning for them from 8:30 to 9:30. But they have really similar stuff. They have homework assignments due Thursday, and you guys have stuff due Thursday. So it's really, really similar. But it's a little bit different. I mean, yeah. Sorry. Yeah. So that's why I switched the times. Oh, okay. Oh, okay. That's what I got you. Yeah. Thanks. Fix the times on that. Hi, Naya. Yeah. Seriously. you might as well just, if you were signing up for taking any classes like next semester or during the spring or summer term or whatever your school does, just use whoever normally teaches the online section. I would take it from them because they're going to have a better idea of how to do online stuff, unless someone's just doing a really good job of transferring to online. Rates. Where's Isaac? He's the one who's always complains about rates. Isaac complains about everything, though. Ooh, computer's chugging. But it should be lower. It's 720p. Isabel, your computer can't handle 720p? Lauren will complain for him. And David, too. Oh, thanks, guys. Maybe he's still sleeping. If someone has Isaac's phone, give him a call. Say, Isaac, wake up. Tune in. And then anybody else, I don't know. I'm sure other people miss the stream, but they don't talk in the chat. So if you don't talk in the chat, I don't really know if you're here or not. Oh. Okay, sorry I wasn't available for questions yesterday afternoon. I was at the school all day, moving and packing up stuff. They needed to do asbestos abatement in my classroom, so I had to get a bunch of crap out yesterday. So I was there all day moving stuff. And I have to do that again today, but I'm going to try to be available for questions and things. Cool. Hopefully you guys are continuing to work on your review books. If you're not, halfway through them by now, you should work more, do more. Oh, my camera's out of focus. Focus, camera. There we go. But yeah. And then, of course, you have the 2017 free response to tomorrow. So let's dive into rates of reactions. Bum, bum, bum. All right, letter A. Isaac's driving somewhere? Okay. All right. Rates. What do we want to say? Rates and we'll just say rates. We'll call it overview maybe. Okay, number 1. Overview. My handwriting's gotten terrible. I'm going to try to do better. All right. So we have so let's just call it definition. Definitions first. All right. First definition. Okay, so a rate is defined as the time for a specific amount of reactants to go to products. Right? Which kind of makes sense. Okay, it's the time for a specific amount of reactants to go to the product. So how long does it take for the reactants to go to products? Really simple, basic definition. What else would we be saying when we talked about the rate of a reaction? Right? So we have to remember that it's based on stoichiometry. Right? If we have, A plus B going to C and D. We talked about how the general expression that the rate of a reaction is equal to the change in the concentration of A divided by A times the change in time. right? So it's how much this concentration of A changes divided by whatever this coefficient is, divided by the change in time. Right? We said that these first ones are negative because they're going down, and as they go down, we know that that's representing a positive rate. We could, of course, repeat this for B, C, and D. Okay, so that's our simple definition of a rate, is it's how does the concentration change versus how does the time change, taking into account the stoichiometric coefficients. Now, there are several factors that affect rate, and we're going to go into each of these factors, but we're just going to list them all here. So some of the factors that affect the rate are going to be things like concentration, temperature, surface area, catalysts, and other factors. Let's say, etc. It's a... I don't know what you're talking about. This is rate equals negative delta concentration of A divided by A delta T little a. So little a plus little bb. So these are deltas for change in. Change in concentration over the change in time. All right, number 2. Yes, Isaac, you're here. Hello. I missed you complaining about rates. Apparently you were driving somewhere this morning. Data and rate laws. All right, let's do some data and some rate laws. So number 2, we can use experimentation to calculate rate. So basically they're saying that rates, experimental rates, can be determined, right? So we can determine the rate of a reaction by measuring some sort of experiment, okay? There he is. There he is. Okay, so we use experiments to calculate the rate. I know, we were missing it. Letter B. So remember that we can use, so rate laws. Rate laws show the order of each, we'll say, reacting species. Right, remember our general format for a rate law is that rate equals K times concentration of A to the M, concentration of B to the N, and then if we have any more, we do that. No, David, don't tell him about ad block. I need that ad revenue. That sweet ad revenue. Okay. All right, so rate laws show the order of each reacting species. Rate equals K times A to the M, B to the N. So the power, so the exponent shows order, right? We said 1 was first order, 2 second order, and then we also could say that 0 was our 0 order. So if something doesn't appear in the rate law, we say that that's a 0 order reaction. That was a total joke about the ad revenue. We do have emotes. What are you talking about? I got sweet emotes, Isabel. You should definitely sub now to get my sweet emotes. Okay. If you are a subscriber, you don't get ads. At least I don't think you do. No, it's probably just your Wi-Fi being bad, Isaac. Yeah, it's probably just your Wi-Fi. Because you're on cellular data. Ooh, Isabel with a follow. She didn't follow me before. Now she follows. Now that I've got ads, now that I've got emotes, I'm worthy of a follow. Okay, so back to this. Exponents show the order. First, second, 1 is the first order. 2 is the second order. 0, or second, 0 is 0 order. So we need to talk about K is the rate constant. And the units change depending on the order. Just to bug you, Sammy. Just to bug you. Just to bug you. No, to be honest, I forgot to do. I should have done 0 first. So, Naya, you can redeem your valence electrons to use emotes, or you can subscribe to get the first emote unlocked. You can use other emotes from other... You can use the general emotes, but in order to use my channel specific emotes... Okay, let's talk about... Let's back to the review. Okay, so K is the rate on usually change depending on the order. I'll do it in the same order. I'll do properly this time. Marin, following doesn't really do much. It basically just makes it so you can see when I go live. Okay, so if for a 0th order reaction, K is going to have the units usually molarity per second or some sort of time, often second. If for a first order reaction, K is going to just be per seconds. And for a second order reaction, K is going to be 1 over molarity times seconds, right? And there's all kinds of ways that you'll see this. Sometimes you'll see it like moles per liter second. Sometimes you'll see it as just per seconds. You'll have molarity to the -1, S to the -1, all those things. Tier 3 subs are $25. If you want to just throw $25 at me, go for it. I wouldn't. Don't use your money for other things. All right, so A, B, C, D, rate constants, orders. You guys always got, I remember in class we got tripped up on the orders. Just make sure that your rate is always concentration per time. And these are always going to be concentrations. And so your K is just usually per time, or sometimes it'll cancel out some of the molarities to go from there. So, okay. So the last thing here is, how do we use the data to actually determine the order? So remember, we could do like, so usually they had like, experiment 1, experiment 2, say we had like A and B, they had initial concentrations, and then they had the rate, and they would say that this was like 1 and 1, and this was 1 and 2, and the rate was like 0.5, and the rate was 2.0, and you would see, oh, as we doubled B and held A constant, the rate went up by a factor of 4. Therefore, the reaction has to be second order with respect to B, because doubling B had a fourfold increase on the rate. That's exponentially, it's squared. So as we doubled this, it went up 4 times. And then we would need some sort of a third experiment to determine what would happen as we changed A. So I hope you guys remember those problems. If not, look them up, see if we can go through them. I can maybe answer questions on those at a later date, but I'm not going to go through those problems right now. But that was kind of where we fit those problems in. Okay. Number 3. Oops. Don't worry, the school board and the high school districts are making sure you guys get A's anyway. So, oh, I skipped a page. Oops. So, number 3. Yeah, David, there's a motion that's went through the school board last night that basically said they were going to make an 85% an A. So I'm still waiting to hear official word on how we're going to implement that, but yeah. Yep. So yeah, I'll send out an official announcement. I'll send out an official announcement later. We're gonna wait till everything's official. Don't freak out now, but probably. You guys were all gonna get A's this try anyway. Everyone gets A's third try because it's easy and just review. As long as you do everything that you need to, you'll get an A. Chill. We'll worry about that later, Lauren. Everyone's focus right now is the AP test. All right. Okay. So let's look at data with concentration versus time. Okay, so these problems, right? These problems are when you have initial rates, but if they give you, if they show you the rate of the concentration versus time, so they show you how the concentration changes over time, this is where we get this idea. So we have graphically, right? So remember, we want to look for a linear relationship looking at 3 different graphs. So it'll always be time on the x-axis, right? And then what are our 3 y-axes going to be if we're talking about rates? Who's gonna get it first? 1 over concentration. That's this last one. 1 over the concentration. Concentration. And the natural log of the concentration. Good job. You guys got it. Okay. So remember, concentration versus time, this is indicative of a... If this is linear, that's going to tell you that it's 0th order. If this one's linear, it's 1st order. And if this one's linear, it's 2nd order, right? So what you'll do is you'll have some data where 2 of these will be, curved and 1 will be linear. So let's imagine like this one's curved and let's just say this one's linear and this one is also slightly curved, right? Something like that. Okay, so this would tell you that, oh yeah, this reaction is 1st order. Okay, they love asking questions like that. I guarantee, I don't guarantee, but there's a very high chance that there will be something like this on the AP test. They absolutely love it. Every time they ask a question about rates, they pull this kind of graphical idea in there. It's super easy points. Should be just something straightforward, easy to remember. I would definitely know this. Yeah, easy money. Okay. Okay, Okay, that's all that. Okay, so don't remember, and then we have our equations. So our equations, we have the concentration of A at time t. They have it written as minus A initially equals negative kT. Concentration of A, the natural log of the concentration of A at time t minus the natural log of the concentration of A initially equals negative kT, and 1 over the concentration of A at time t minus 1 over the concentration of A initially equals kT. Okay, so remember this is our 0th, first, and second. Now, on the equation sheet, they give you these ones, but they don't give you that one. I don't know why, but they give you these two equations and they don't give you that equation. So just remember that going from the first to the 0 is really easy. You just drop the natural logs, right? So 0th order is concentration versus time. First order is natural log versus time. Second order is 1 over versus time. So these are the equations that describe these graphs. So you would use each equation for whatever order it is. Yeah. So if you were trying to figure out, what the concentration will be at a certain time, you would figure out what the order is, and then you would plug in, okay, what's the initial, what's the time you're trying to find, what's K, and then you could predict what the concentration is going to be. So these are all variables that you would plug in, depending on the problem. The other thing they kind of mentioned just randomly is half-life. Half-life really only applies to first-order reactions. White from the background. Applies to first order. And the equation for a first-order half-life is that the half-life time, T1 half, is equal to the natural log of 2 over K, which the natural log of 2 is 0.693 over K. Let's see. Oh, half-life 2. So is the second order KT not negative? No, it's not. It's positive. And if you remember back to, I doubt you remember back to this, but we did all the calculus that showed the derivation of these equations. And in the calculus of this, it ended up being positive because of the way that you integrate 1 over x squared. But you don't have to remember that if you don't remember that. But you do know that it is positive, and that I didn't make a mistake there. It is positive. Okay. So I guess we should kind of just mention radioactive decays are first order. Right, and they're important for understanding, radiochemical dating and all those other things. But you don't have to know much more about it other than that we use first order half-life for radioactive decay. Okay, cool. Done with that. Next. That was letter A. This is letter B. Big letter B. I want to say we're going to call this collision theory. Right. So if you remember, collision theory is the idea that in order for a reaction to occur, particles and molecules have to physically collide with each other. So if we have elementary reactions, right? So let's just say, A plus 2B makes C. Then the rate for this reaction is equal to K times the concentration of A times the concentration of B squared, right? So remember, for an elementary reaction, you can take the coefficients and determine the order, right? Now, you can't assume a reaction is an elementary reaction unless given, okay? It could be a reaction that happens in multiple steps, and if it's a multi-step reaction, you can't determine the rate law. But if it's an elementary reaction, we know that the rate is equal to the coefficients from the equation. Okay, now what does this mean? This means that atoms and molecules collide and react in a single step. Okay, so that's what we mean by an elementary reaction. All right, our atoms and molecules are colliding in a single step. And then this kind of reaction I've given is actually pretty rare, because this would be a third order overall, which probably wouldn't happen. It would be more likely that like something would combine with itself, or it would just react with two things. But yeah. Okay, cool. So that's all for that. Number 2. Okay, so we have our, I guess we'll call them collision factors. So what were the factors about collisions that affected the rate of a reaction? Concentration, right? And the reason why concentration, okay, and it's not just remembering what they are, it's remembering why they are, right? So concentration, because a greater concentration was more collisions, right? Particles and molecules will collide more frequently if they're at a higher concentration. The next one people are listing are, I don't know about elasticity, Haley. Energy is an important one. Yeah, energy is an important one. So energy, and we can't necessarily affect, the way we affect energy, specifically kinetic energy, is with temperature. Right? So a greater temperature is not only more collisions, but the bigger thing is that they have more energy. And then the other thing that you guys don't remember was the orientation. Right? We needed a proper orientation in order to get them to get the molecules to work, right? So we needed so the simpler your molecules are, the less that this orientation matters. So, and the more complex they are, the more difficult it is to line it up, the slower your rate of reaction is going to be. So they had these curve things, right? So sometimes they'll show kind of a curve that looks a little bit like this, right? And they'll maybe say that, okay, so if this is, say this is energy here, and this is the fraction of molecules, right? And they're going to say that like this point right here, right, we'll say that this represents the minimum energy for reaction. Okay, minimum energy for reaction, right? So that means that if this represents all of the molecules in your sample, only the atoms and molecules that are up here right, have enough energy that they can collide. Sure. I have a Logitech. What do I have? A Logitech HD 1080p. I don't actually know the actual brand of it. And then microphone. I don't have a. It's just clipped onto my monitor. And then my microphone, I use a HyperX stand mic. And my actual webcam or my document camera is an Aver Vision F17 8M. Okay, so back to this, right? So atoms and molecules that are above this minimum threshold will have enough energy to collide. So let's see, is it have enough energy to collide or enough energy to react when they collide? Oh yeah, sorry, that's say they have enough energy to result in a successful reaction when they collide. Thanks, DJ. So this is the minimum amount of energy for a successful collision, I should say. All these molecules are colliding with each other, but this is the minimum for a successful collision that will result in a reaction. Okay. So what we would say is that if we increase the temperature, right, the curve, let me draw it in a different, the curve changes to something like this, right? So this represents a higher temperature. And so the minimum energy is still going to be the same, but now notice we now have a much greater fraction of the molecules that have enough energy to react. Okay. So that's kind of how a temperature will affect this. Another thing we can think about is we'll get to catalyst. Actually, we'll talk about catalyst later. So a greater fraction of the molecules will have enough energy to react if we raise the temperature because the curve, the distribution changes. So the curve gets more shallow with higher temperature. Yeah, because you have a greater fraction of your molecules that have a greater energy at higher temperatures. So it flattens and broadens as you get a higher temperature. So it's the fraction of the molecules that react or that possess enough energy to react is the technical way to say it. So a greater fraction of the molecules possess enough kinetic energy that when they collide, it will result in a successful collision or a reaction. Yeah, the terminology on rates is a little tricky. You got to be careful on how you phrase things. So speaking of, let's actually talk about this minimum energy for reaction. That has a name. It's called activation energy. Oh, sorry. That's why this is D. A, B, C, D. This graph is D. Orientation is just the complexity of the molecules. If they're more complex, you'll have less reactions, less successful collisions. I kind of glanced over that. Sorry, I really wanted to get to the graph. Okay, so activation energy, right? So we could also think about another graph representing activation energy. If we do energy on the y-axis, and we do, sometimes this is called all kinds of things. Sometimes it's called the reaction coordinate. Sometimes it's called reaction progress. I like calling it reaction. I like calling it reaction progress. Okay. So for something like an exothermic reaction, you would see something like this guy, right? Where you have, let's say we have A and B. This is the reaction. A goes to B. Right? Now, on this graph, where is the activation energy? Yeah, so it's the peak. Yeah, so it's between A and the peak. So this amount right here represents our E sub A, activation energy. Right? So it's showing that in order to react, we have to have enough energy to get up to here. Now this guy up here, right, that's called the activated complex. Right? The activated complex is where all the bonds in the reactants are beginning to break and all the bonds in the products are beginning to form. It's the highest energetic state between reactants and products. So it represents, our distance from our reactants to the activated complex is the activation energy. Right? We have to form the activated complex in order for the reaction to progress. So in order for us to kind of get up and over this bump, we have to have this amount of energy. So if molecules collide and they don't, you can kind of imagine it as like a ball going up and over. It's not a great analogy, but it's okay. Yeah, it's the weird in-between stage. So if we think about a reaction involving like hydrogen and iodide, so we have H2 and I2. The intermediate complex looks something like this. Right? Which is really, really weird because these bonds are breaking and these bonds are forming because we're forming HI. And so we get this weird kind of almost square looking molecule that is incredibly unstable. It doesn't last for more than a fraction of a second. And it's that in between as our hydrogen bonds are breaking and our iodine bonds are breaking and our HI bonds are forming. Okay, cool. Now, side note, what is the activation energy for the reverse reaction, and how does that compare? How would the activation energy for the reverse reaction compare to the activation energy of the forward reaction? Yeah, so the reverse reaction has a much greater activation energy. We'll call this EA, maybe we'll call it -1. Right, so the activation energy of the reverse reaction is much higher because in order to go from B to the activated complex, it's a much bigger gap. Yeah, there's a lot of stuff here, sorry. But yeah. Okay, questions on these graphs. Again, they love asking these graphs too. Wouldn't it be like the amount of energy released plus the activation energy forward? Yeah, so if you wanted to calculate it mathematically, what do we call this difference? The difference between A and B, difference between the energy of our reactants and our products. Isn't that called something? Isn't that special? Hey, Zach's got it. Delta H. Okay, so this is the delta H of the reaction. In the forward direction, it's going to be negative because we're losing energy, and the reverse reaction is going to be positive. And so this reversed activation energy is actually our delta H plus our original activation energy. It's the same gap, the same distance. So yeah, we do need to mention delta H. Okay. While we're here, let's go ahead and just quickly talk about catalysts. Well, I'm going to talk more about catalysts later, but what would a catalyst do to this graph? How does a catalyst increase the rate of a reaction? It lowers the activation energy, right? And so a catalyst would come in and maybe alternate this pathway somehow to give us a lower activation energy. So notice a catalyst does not change delta H. use a better term. Yeah. So a catalyst doesn't change delta H, it only changes the activation energy. So our delta H remains constant. That's kind of an important idea to remember. What it does is it basically makes the activated complex, it gives some sort of alternate activated complex, which lowers the activation energy. So this is important, understanding that's a catalyst. We'll talk more about catalyst in a minute, but I just want to say that that's kind of our catalyst idea. Okay. Next, letter C. Mechanisms. Okay, so let's talk about a mechanism in general. Okay, a mechanism shows a multi-step process. So let's say we had our overall equation is A plus B goes to C. All right, that's our overall equation. We could propose a mechanism where we could say that A goes to D, and then D reacts with I don't know. Yeah, we'll just make it really simple. D reacts with B to make C. And we could say that this was the slow step and this was a fast step. Okay. So we could say that, okay, let's imagine this is our overall reaction, and then we're going to propose this mechanism where we have step 1 and step 2. So apparently in step 1, A turns into some other weird compound, and then that weird compound is what actually reacts with B to make C. Okay, and we can say this is a slow step and this is the fast step. All right. Now, what do we know about a mechanism, right? What is important? Okay, notice, okay, the steps add up to the overall. Right? A proper mechanism has the steps that add up to give us our overall equation. If we add these two together, D cancels, it's known as an intermediate. And yeah, the slow step is the only one that matters. Okay, the reaction is going to be as fast as the slow step, right? The slow step is known as the rate determining step. So we're going to add that on there. The slow step is the rate determining step. You can think about an assembly line, right? If you have an assembly line where you're trying to make some sort of a product, whatever the slowest step is along that assembly line is going to determine how quickly you can make stuff, right? If you increase all the other steps in the process, but you still have one step that takes, an hour, that's going to determine how quickly you can make your product. Okay. Right, slow step to rate determining step. In our case, we would call this D compound, we would call that an intermediate. It doesn't appear in the overall expression, but it does appear in the mechanism. So, yeah. Okay, I think that's all I wanted to say about that. So that's our general. And so then here, we can write rate laws. Right? So if this was our mechanism for this reaction, what is the rate law for this reaction? We would say that rate equals, for our example above, using this mechanism, what's our rate? Yeah, K times the concentration of A. Right? And it's weird because if I just gave you this overall expression, right, you might say, oh, it's got to be A and B, A times B. But the thing is, according to this mechanism, our slow step just has A reacting. And so the rate is determined by the slow step, and we just use the coefficients from the slow step to tell us the order. And so because B doesn't enter the picture until the second or the fast step, B doesn't actually matter in terms of the rate or the rate law. And so the rate here is K, that's a terrible K, K times the concentration of A. Let's see. I want to make sure I'm understanding this right. For action mechanism, each elementary step is irreversible, or in which the first step is rate limiting. The rate of their action is set up by the molecular to the slowest elementary. The rate limiting. Yeah. Okay. Cool. We also talked about the weird case where, like, if the first step was like a fast equilibrium that you could plug in and do that. I think it's unlikely that the AP test will ask you a question about that. It's more likely that they're going to give you mechanisms and they're just going to use the first step as the slow step. That's a much higher likelihood than having like a fast equilibrium like some of the more complicated mechanisms we did. So kind of just, mention this. Use coefficients, use the slow step. Okay. Okay. Cool. All right, let's talk about catalysts. We're going to try to do this real quick in the last couple minutes. So a few things I want to mention about catalysts that we didn't talk in a bunch of details in class. We kind of have talked about how a catalyst lowers the activation energy. Cool. So we'll mention that first. Catalysts are not consumed in a reaction, but they provide an alternate path to lower activation energy. Okay. Now, the AP test does want to make you aware of a couple different types of catalysts. So they have three types they mention. They mention binding catalysts, surface catalysts, and bonding catalyst. Binding, bonding, and surface. Right? So those are kind of the three catalysts. The surface catalysts, in my mind, are the easiest to understand. This is like if you have the reaction of, say, hydrogen and iodine making HI, and you add something like usually some sort of a metal, maybe like platinum or something. Right? What the platinum does is it provides a spot for the hydrogen molecules to kind of go on to the surface. And these hydrogens, as they're on the surface, they kind of are lined up and they're ready for the iodines to come in, and they can react easier. Basically, the surface, this platinum surface, provides kind of a better way to do that. You would have to have the first step. So, Sammy, to answer your question, you would have to have the first step be an equilibrium step. And the rate would actually just be rate equals k times a, or yeah, k times a to the first, b to the first. I'd have to have more time to go through that. Yeah. But like I said, if I'm going to put money on it, I would bet that if they ask you about a mechanism, that the first step is going to be the slow step. Okay, let me talk about the other two catalysts real fast in my last 5 minutes. So these ones actually, they kind of, what they'll do is all catalysts kind of affect the orientation. And so for a binding catalyst, it binds to one of the reactants to make it react better. So it'll react on like a molecule by molecule basis. And so you'll have kind of an individual molecule. The catalyst comes in and forms kind of a bond, or it binds to it, kind of wraps around it, and that allows it to react a little better. These are our enzymes. For those of you that are in like bio or AP bio, this is how enzymes function. Enzymes are binding catalysts. These are when we talk about bonding, this is more of like an acid-base idea. So sometimes you'll like have some sort of organic molecule, and then if you put it into an acidic conditions, that will cause it to gain or lose protons. Oh man, I'm sorry to hear that, Ziju. Try it. There's a lot of good resources on the AP website if you really can't do it. The College Board is actually doing streams and stuff on YouTube, so I would definitely look into those. That's a good reminder for all of my AP Chemistry kids as well. There are some good streams up on the College Board YouTube channel. I don't love the guy who presents it, but he does an okay job. He does a pretty good job, and he's got some good insights. So it would be worthwhile if you're looking for more stuff to study to go and to watch the College Board chemistry streams as well. He's doing kind of like a unit by unit review like mine, like I've been doing. So he'll add some more insights that I don't necessarily go through. All right, bonding catalyst. Acid base, you can make something basically gain or lose a proton to react better. Basically, it kind of helps to usher along. Oh gosh, no, I should not be president of College Board. That sounds like a nightmare. I wish they would consult me on more chemistry questions. That would be great. But being in charge of College Board does not sound like a fun job. This is actually it for Unit 5. This is the end of Unit 5. That's was kind of a quick rundown of rates. A few things to remember. Hopefully this helped you guys remember some things. A couple things came back. Work on the 2017 free response if you haven't done that yet. We're going to go through that on Friday. I am still planning on teaching you guys on Friday, even though a couple teachers are taking the day off because of parent-teacher conferences. Whatever. I'm going to continue to teach on Friday. I'm going to send out a calendar sometime tomorrow to let you know what we're going to do in May. Yeah, I want all the power, Isabel. That's what it is. I want to be able to make changes on what should be on the AP test. But yeah, no, I'm going to continue to teach on Friday. Make sure you guys tune in, watch the YouTube streams if you need extra help, work through your review books, work through the free response exams, and then make sure to ask me any questions on Friday. Cool. Use those valence electrons, Isabel. Okay, have a great day, guys. Happy studying. Keep working. We've got 3 weeks left that we really just need to keep grinding it out. I know it's hard to find motivation right now, but you guys are all capable of passing this test, so let's make sure we get it done. Okay, have a great day, guys.